All right, guys, it is now time for the third technical section in which we talk about encryption and decryption. So here's our funny internet picture of the day. If you don't understand that joke, ask a gamer. So, encryption and decryption. Essentially, the simple version of this is if I have a message I want to send to somebody else, and I want to make sure that nobody else intercepts and can read that message, I encrypt it. In other words, I take the plain text, the message that I want to send, and I want the recipient to read, and I scramble it in some patterned way so that the person at the other end who understands the pattern can recreate that plain text from the encrypted text. The process of taking it from plain text into encrypted or ciphertext is called encryption. The process of then taking that ciphertext or encrypted text and returning it back to the plain text is called decryption. So it's just both ends of the process. We scramble with encryption, we unscramble with decryption. Okay? There are three big purposes for encryption. The first is authentication. In other words, we want to make sure you are who you say you are. If you can't decrypt this thing, you are not who you say you are, and thus you have no right to see it. Okay? In addition, the flip side of that is that there's non-repudiation. So if you used your particular password to encrypt something, we know it was you who sent it. You can't say it wasn't you. This is how things like digital document signatures. If you've ever had to send something to a health care provider, or if you bought a house or something, they do these kind of digital signatures, which are essentially using these encryption techniques. And thus, so it's kind of the thing where if you know the password to do the thing, then that is authenticating it as being sent from you. Okay? The second is confidentiality. This is the one most people think of. Okay? This is keeping data secret. So like in warfare, if I want to send a message to my troops that like they need to attack this place at this time, I want to make sure that if the enemy captures that message en route from me to the troops that I'm trying to send it to, I want to make sure the enemy can't read it so they don't know that the attack is coming at such and such place and such time. If they're ready for me, that would be very bad. So confidentiality, keeping the text of that message secret. This can be anything from financial transactions online to troop movements to love letters you send your boyfriend and girlfriend. There's lots of different reasons why we want to keep data secret, and encryption is a really good way to do that. And then finally, there's integrity. Using encryption techniques, we can make sure that the message wasn't changed between point A and point B. Because if the message somehow gets changed, then the decryption process won't work anymore. So if we can encrypt it using a certain key and then decrypt it using that certain key, we know that the message wasn't changed in transit. Okay? Traditionally, there have been a bunch of different methods of encryption. The simplest and easiest was substitution. This is the one, we all did it as kids, where, A equals 1, B equals 2, C equals 3, all the way up to Z equal 26. And then you write out your message with the numbers, and then you send that to another kid, and the kid gets it and retranslate those numbers back into letters and reads the message. That's a very simple substitution cipher. Okay? But it doesn't have to be that simple. You can get a lot more complicated with substitution ciphers. For instance, you can have A equals R, B equals exclamation point, C equals either E or a period. Things like that that complicate substitution ciphers much past A equals 1, B equals 2, C equals 3. But no matter what you do, there are always going to be even people can crack substitution ciphers if given enough of the ciphertext and enough time. Computers can do it really easily. So those have fallen out of use with any kind of serious encryption schemes. You can also do transposition, which is essentially shifting letters some direction to the right or left along the alphabet line. So, if the transposition code is 2, that means you shift every letter 2 to the right when you're encrypting and 2 to the left when you're decrypting. So an A shifted 2 to the right becomes a C when you're encrypting. When you're decrypting, an F, you move 2 to the left, that becomes a D, right? And you can get transposition codes that are multiple digits long. So the first letter you see in the line, if the code is 1, 2, 3, 4, 5, when you're encrypting, the first letter you shift 1 to the right, the second letter you shift 2 to the right. So if the message is Kevin, the K gets shifted 1 letter to the right, the E gets shifted 2 letters to the right, the V gets shifted 3 letters to the right, etc. But again, if you have enough ciphertext, even humans can figure out the transposition code. Okay? Obscure languages have also been used for encryption purposes. In World War II, there was a famous incident where the U.S. Navy and the U.S. Marine Corps used the Navajo language to encode their communications between the ships and the Marines on shore. And what would happen is, for every ship had a Navajo code talker who spoke Navajo and was able to sit on the radio on the ship. And then every Marine unit had at least one Navajo code talker that would go with the Marines. And then if, the lieutenant of the Marines said, hey, we need to tell the ship this, this, and this, the person who was with him would translate that into Navajo, send it over the radio to the code talker back on the ship, who would retranslate it back into English and send it on to where it went. That meant that the Japanese could capture all the radio communications they wanted, but since Navajo was such an obscure language, the Japanese couldn't find anybody to translate it back into Japanese. So it was an effective way to encrypt the communications during World War II. Also during World War II, the Nazis used a really, really kind of ingenious cipher device. These are essentially mechanical ways of encrypting a certain text using this device. In World War II, the Nazis had the Enigma machine, which was essentially, it had a whole bunch of different gears and rotors and a keyboard, what looked like a keyboard on the front, and then lights on the back corresponding to each letter. So what you would do to encrypt, you would push, if you wanted to encrypt Kevin, you'd push K and a light would light up saying what you should encrypt that letter as. Maybe it's B. So you write down a B. Then you push, but the rotors turn after every push. So now it changes what the substitution code is. Then you push E and another letter lights up. Then you push V and another letter lights up and the rotors turn. And then you push I and another letter lights up and the rotors turn. So it was essentially a substitution cipher, but monumentally complex because it has this machine for the encoding and decoding procedures. So not only did you need to understand, so you needed a machine, but then you also needed to know what the starting rotor position was for the day. And every day, they would set the rotor position to a different starting position and do all the day's encryption and decryption using that starting rotor position. And then at midnight, they would change the rotor position and do all their encoding for that day. So even if you captured one of these machines, you still couldn't use it to decrypt communications that you had captured if you didn't know the starting rotor positions for that day. To break this code, the British got a guy named Alan Turing, who was an absolutely brilliant, he's commonly referred to as the father of computer science. Absolutely brilliant guy. And he built one of the world's first computers, depending on how you define the term computer, in order to break that Enigma code and figure out what the rotor positions are to start each day so that they can decrypt all these communications. And he succeeded. The team led by Turing at Bletchley Park in the UK succeeded in deciphering this Enigma code. And the Nazis were so sure of the security of that device that they didn't even contemplate the fact that maybe the Allies had broken their code. So Alan Turing did a lot to win World War II. There's a really great movie about that, the Enigma device and Alan Turing and the creation of that computer that he made. It's called The Imitation Game, starring Benedict Cumberbatch. Definitely go see that movie if you haven't. It is absolutely wonderful film. But modern encryption. So all of those techniques that I just described were what's called symmetric encryption, meaning you use the exact same process for both encryption and decryption. As such, both sender and receiver have to both know the same key. And if, say, I'm a military commander and I have a ship out at sea and we're using one method of symmetric encryption, but oh wow, I found out that the enemy has completely broken our encryption system. We need to change our key. We need to completely change what that key is. How do I tell the ship at sea what the new key is without the enemy capturing it and figuring it out? You can't. You know they have broken the old encryption system, so you can't send it over using the old encryption system. You can't send it using the new encryption system because the people on the other end won't know how to decrypt it. You're out of luck until that ship returns and you can tell them in person. So in the 70s, some mathematicians decided to fix that problem. And they came up with a really ingenious system that is based on math that I don't even pretend to understand. Again, you need kind of a PhD in mathematics to understand some of these concepts. But they came up with what they called asymmetric encryption, which is brilliant in its design and simplicity, but based on some really complicated mathematics. But essentially, with asymmetric encryption, everybody creates two keys. And usually this is done in the background, so it's not, users don't have to do this consciously. It's done kind of in the background by these programs. But every time a user kind of creates an account, there are two keys generated. The first is a private key that only they know. Think of that key like a password. Only you know that password. But the other one is a public key, and the public key everybody knows, right? You specifically advertise as much as possible what your public key is. Now, the way this works is if you encode or encrypt a message with one of the two keys, you can only decrypt it with the other. Now, look at this chart. Alice has a private key and a public key. Bob has a public key and a private key. They want to communicate without either knowing the same secret key, right? So in symmetric encryption, both sender and receiver have to know the same secret key. With asymmetric encryption, nobody knows each other's secret keys. They only know each other's public keys. So Alice wants to send a message to Bob. So she encrypts her plain text with Bob's public key. Then she sends it to Bob, who decrypts it with his private key. Because remember, if you encrypt using one, you have to decrypt using the other. So Alice used his public key to encrypt it, which is, obviously she knows Bob's public key because that's advertised. And Bob uses his private key to decrypt it. Now Alice has communicated with Bob without knowing Bob's private key, without knowing the same key. It didn't have the same key problem. Now Bob wants to reply. So he takes his message, encrypts it with Alice's public key, sends it to her, and she decrypts it using her private key. In this way, nobody has to know anybody else's secret key, like they did under symmetric encryption processes. Everybody keeps their own secret key that only they know. This is a really, really brilliant method of encrypting communications because you don't have to share with anybody like you do with all the symmetric encryption processes. So this kind of revolutionized encryption and security for computers. They didn't actually have commercial software using this process until the 90s. But in the 90s, they were able to utilize this system, and this is the basis for essentially all of e-commerce today. So Amazon and Etsy and Wish and all those, any internet company that takes money or deals with credit card information or any of that stuff uses this kind of encryption because that means they don't have to give out their encryption scheme to the people who make like web browsers and stuff. Because any secret shared by more than 2 people is not going to remain secret for long, right? So, but what's really cool about asymmetric encryption is it has other uses than just securing messages. It has more uses than just the confidentiality part. So imagine a situation where I encrypt something using my private key and then post it on the internet. And now anybody who wants to can decrypt that thing using my public key. That is not very good at keeping the information confidential. But remember, there's a lot of other reasons to use encryption, not just confidentiality. So if I encrypt with my private key, and then anybody who wants to can decrypt using my public key, that is using the exact same process, but instead of using it for confidentiality, we're using it for non-repudiation, and we're using it for message integrity. So if they can decrypt that file or that message using my public key, they know that I am definitely the one that sent it, and that it hasn't been changed by anybody since I encrypted it. That's how things like digital security certificates work, right? So Microsoft will send out a patch for their, to fix their operating system. So if you want to patch Windows, you have to download it from Microsoft. But they use this process. They encrypt that patch using their private key. And then every Windows user gets to kind of automatically decrypt it using their public key. As such, your computer is very, very certain that that patch came from Microsoft and it hasn't been changed by anybody else since Microsoft sent it out. So this asymmetric encryption system has a lot of really cool, really interesting, different uses throughout the internet. So that's the end of part 1. I'll be right back and talking about steganographic data.